Tonight, we're going to explore something you experience every single moment of your life, but probably never think about: pressure. Right now, as you're reading this or listening to this, there's roughly 14.5 pounds of force pressing down on every square inch of your body. The entire weight of Earth's atmosphere is pushing on you from all directions. You don't feel it because the fluids inside your body are pushing back with equal force. It's a perfect balance, a standoff between the air outside and everything inside you. But here's what's remarkable. Here's what's going to change how you see the ocean. If you descend just 10 meters below the surface of the sea, just 33 feet, that pressure doubles. Go down another 10 meters and it doubles again. Keep going, and the pressure increases at a rate that quickly becomes incomprehensible. At the deepest point in the ocean, the pressure is over 1,000 times what you're experiencing right now. More than 16,000 pounds pressing on every square inch. 8 tons per square inch. If you tried to build a chamber large enough to hold a person that could generate that much pressure, the engineering required would be virtually impossible. And here's the twist that makes this so fascinating. We cannot replicate these conditions on land. Not really. Not at the scale nature creates them. The ocean generates pressures through sheer volume, through the weight of water stacked miles high, through a mechanism so simple and so massive that our technology struggles to match it. Before we dive in, if you find this exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now let's begin this journey into understanding why hydrostatic pressure is a force we simply cannot replicate. Consider what pressure actually is. We use the word all the time: peer pressure, blood pressure, pressure to perform, the pressure of deadlines. But in physics, pressure has a very specific meaning. It's force distributed over an area. Push on a wall with your hand and you're applying force. But the pressure you're creating depends on how that force spreads out. Push with your entire palm, and the force distributes across maybe 20 square inches. Push with just your fingertip and that same force concentrates into less than 1/4 of a square inch. Same force, very different pressure. This is why a knife cuts and a hammer smashes. The knife concentrates force into a thin edge, creating enormous pressure along that line. The hammer spreads force across a broader surface. Pressure is measured in pounds per square inch or pascals or atmospheres. 1 atmosphere is the pressure exerted by Earth's atmosphere at sea level, approximately 14.7 pounds per square inch. This is what your body's designed for, what you've adapted to through millions of years of evolution. Your cells, your tissues, your organs, all calibrated for this specific pressure. Change it significantly and problems start immediately. Now here's where the ocean becomes interesting. Water is 800 times denser than air. A column of seawater just 10 meters tall exerts the same pressure as the entire 550-kilometer thick atmosphere above it. Think about that for a moment. 10 meters of water equals 550 kilometers of air. The ocean achieves in 33 feet what the atmosphere requires 340 miles to accomplish. This is because water molecules are packed far more tightly than air molecules. More mass in the same space means more weight pressing down, and weight creates pressure. This is hydrostatic pressure. The prefix hydro means water, static means at rest. Hydrostatic pressure is the pressure exerted by a fluid at rest due to the force of gravity. Every layer of water presses down on the layer beneath it. The deeper you go, the more water above you, the more weight, the more pressure. It increases linearly with depth, predictably, relentlessly. For every 10 meters you descend in the ocean, the pressure increases by 1 atmosphere. At 20 meters, you're under 3 atmospheres of pressure. 1 from the air above the water, 2 from the water itself. At 100 meters, 11 atmospheres. At 1,000 meters, 101 atmospheres. At the average ocean depth of 3,800 meters, the pressure reaches 381 atmospheres. 381 times what you're experiencing right now. But the ocean doesn't stop at the average depth. There are places where it goes much, much deeper. The Mariana Trench in the Western Pacific Ocean plunges to nearly 11,000 meters below the surface. Its deepest point, Challenger Deep, sits at approximately 10,935 meters down, give or take a few meters depending on which expedition's measurements you trust. At that depth, the pressure reaches approximately 1,093 atmospheres. Let me put that in perspective. Imagine an elephant. An adult African elephant weighs around 6 tons. Now imagine that elephant standing on your thumbnail. That's approximately the pressure at Challenger Deep, except it's not just pressing down, it's pressing from every direction simultaneously. Up, down, left, right, from every angle. The water surrounds you, crushes you from all sides with equal force. Or here's another way to think about it. Stack 100 elephants on top of each other, then somehow balance that entire column on a single postage stamp. That's the pressure we're talking about. 16,000 pounds per square inch, 1,000 times atmospheric pressure, the weight of the entire ocean pressing down on a tiny point. And this pressure exists naturally, constantly, in the deepest parts of the ocean. It's just there, a consequence of gravity acting on water, no machinery required, no human engineering, just mass and gravity doing what they do. Now, you might think we could easily recreate this in a laboratory. After all, we've built particle accelerators that smash atoms together at nearly the speed of light. We've created temperatures hotter than the surface of the sun. We've generated magnetic fields millions of times stronger than Earth's. Surely we can make a chamber that squeezes something with the same pressure found at the bottom of the ocean. And you'd be partly right. We can create high pressure in small chambers, very small chambers. But here's the problem. The smaller the chamber, the easier it is to make high pressure. The larger the chamber, the exponentially more difficult it becomes. A pressure vessel works by containing fluid and preventing it from expanding. The walls must be strong enough to resist bursting. The thicker the walls, the more pressure they can contain. But thickness adds weight, and weight requires stronger support structures, which add more weight. You end up in an engineering spiral where each increase in size requires disproportionate increases in wall thickness and structural support. The largest pressure chambers that can reach full ocean depth pressures are measured in inches, not feet. We're talking about chambers maybe 16 inches in diameter, perhaps 30 inches long. You could fit some equipment inside, some instruments, but not a person, not even close. You certainly couldn't fit a submersible. The pressure vessels used to test components for deep-sea exploration are large steel cylinders with walls several inches thick. They can simulate the pressure, but only for objects small enough to fit inside. And even these chambers have limits. The deepest rated chambers can reach maybe 30,000 pounds per square inch. That's impressive. That's roughly equivalent to the deepest parts of the ocean. But these chambers are small. Think about the numbers for a moment. If you wanted to make a pressure chamber just large enough to fit a person sitting down, maybe a cylinder 6 feet in diameter and 8 feet tall, you'd need walls incredibly thick to withstand Challenger deep pressure. Steel has a tensile strength of around 60,000 pounds per square inch for high-grade alloys. To contain 16,000 pounds per square inch internal pressure, using the standard formula for cylinder wall thickness, you'd need walls several feet thick, not inches, feet. That's an enormous amount of steel. The weight would be measured in hundreds of tons. The cost would be astronomical, and that's just for a chamber barely large enough for one person. If you wanted to make it big enough to contain a small submersible, say 10 feet in diameter and 20 feet long, the wall thickness requirements increase dramatically. You might need walls 4 or 5 feet thick. The total weight could be thousands of tons. Moving it would require specialized equipment. Installing it would be a major construction project. Operating it would require massive pumps to pressurize such a large volume, and maintaining it would be an ongoing challenge. Any tiny crack, any flaw in the welds, any weakness in the material could lead to catastrophic failure under those pressures. Testing the chamber itself would be risky. How do you verify that a vessel this large can safely handle the pressure? You can't exactly build a test chamber for your test chamber. If you wanted to make one large enough to hold a person, large enough to test a full-size submersible, large enough to truly replicate the environment of Challenger Deep, the engineering becomes nearly impossible. The walls would need to be feet thick. The weight would be enormous, the cost astronomical, and even then you'd face fundamental limits in material science. Steel can only be so strong before it fails. There's a point where making the walls thicker doesn't help because the steel itself can't handle the stress. You'd need exotic materials, titanium alloys, carbon fiber composites, each with their own limitations and astronomical costs. And here's something else to consider. In the ocean, the pressure is uniform. It presses from all directions equally. In a pressure chamber on land, you're typically pressurizing a fluid inside a rigid container. The container walls bear all the stress. They're being stretched outward by the pressure inside. It's a fundamentally different mechanical situation than what exists in the deep ocean. In the ocean, Everything is surrounded by high pressure. There's nowhere for the pressure to escape to because everything around you is also under that same pressure. It's a self-equilibrating system. The pressure exists because of the sheer volume of water above. To replicate that exactly, you'd need an equivalent mass of something pressing down. You'd need your own ocean. So when we say we can simulate deep ocean pressure, what we really mean is we can create similar pressure readings in a small test chamber for brief periods. We can test how a particular seal responds, how a specific material behaves, how an electronic housing performs, but we cannot recreate the actual environment, the scale, the totality of it. We cannot build a room where a person could experience 1,000 atmospheres of pressure and survive. The ocean does this naturally, effortlessly, in volumes measured in cubic kilometers. We struggle to do it in volumes measured in cubic inches. Let me tell you what happens to things when you expose them to this kind of pressure. Start with something simple, a foam cup, the kind you get coffee in. These cups are made of expanded polystyrene foam. The foam is mostly air, tiny bubbles of air trapped in polystyrene walls. When you take a foam cup and attach it to a deep-sea submersible or remotely operated vehicle and send it down to the ocean floor, something remarkable happens. As the cup descends, the increasing pressure compresses the air bubbles. Inside the foam, the air molecules are forced closer together, the bubbles get smaller, the foam gets denser. At the surface, Boyle's law tells us that the pressure and volume of a gas are inversely related. Double the pressure and the volume halves. Triple the pressure, and the volume drops to 1/3. At Challenger Deep, the pressure is over 1,000 times surface pressure. The air in those foam bubbles compresses to less than 1/1000th of its original volume. The result is striking. A foam cup that started out 4 inches tall might come back 2 inches tall, perfectly proportioned, just shrunken. Like someone put it in a magical shrinking machine. The polystyrene itself doesn't shrink, it's a solid. But the air spaces inside the foam collapse under the pressure. The cup weighs the same, it's made of the same material, it's just compressed, dense. The transformation is so uniform, so complete, that people who work on deep-sea research vessels often send foam cups down attached to their equipment as souvenirs. They'll draw pictures on the cups before they go down. When they come back up, the drawings are still there, just smaller. It's a tangible demonstration of pressure's power. Scientists have sent down foam mannequin heads, foam blocks with names carved into them, all sorts of foam objects. They all come back perfectly miniaturized. The proportions remain exact. A circle stays a circle, just smaller. A square stays a square. The compression is uniform in all directions because the pressure acts uniformly from all sides. This is different from, say, putting something in a vise, which would compress it in one direction and deform it. Ocean pressure compresses equally from every angle, resulting in this perfect, proportional shrinkage. The phenomenon is so reliable, so predictable, that it's become a tradition on research vessels. Crew members will decorate foam cups with markers, writing messages, drawing pictures, signing names. The cups go down attached to equipment heading to the deep ocean floor. When they return, these tiny compressed cups become cherished mementos, evidence of where they've been, proof of the extreme conditions they've witnessed, even if only indirectly. Now, consider something different. Consider air itself. If you could somehow take a balloon filled with air at the surface and bring it down to Challenger Deep, the balloon would shrink to almost nothing, 1/1000th of its original volume. That's assuming the balloon material could even withstand the pressure, which it couldn't. Rubber would compress and fail long before reaching those depths. This is a major problem for anything that contains air at ocean depths. Your lungs, for example, are air-filled spaces. If you were somehow naked and unprotected at Challenger Deep, your lungs would try to compress to 1/1000th their normal volume. Your chest cavity would collapse, your rib cage would fold inward, the air inside your body would compress until the pressure inside matched the pressure outside. Except you can't compress that far, your bones would break, your organs would rupture, you'd be crushed instantly. This isn't theoretical. We know exactly what happens to air-filled spaces under extreme pressure because we can observe it in controlled ways. When submarines operate at depth, any air pockets that aren't equalized with the interior pressure will compress. If a submarine has a flaw, a tiny air gap somewhere in its structure, that gap will compress as the sub descends. If the sub goes too deep for its design, if the pressure exceeds what it's built for, compression can cause catastrophic failure. The hull might buckle inward, seams might rupture. The results are usually fatal for anyone aboard. History has several examples of submarines that exceeded their crush depth and were destroyed by pressure. The vessels literally implode, crushed inward by the water pressure. The air inside compresses catastrophically. The event happens in milliseconds. There's no time to react, no chance of survival. One moment the submarine is intact, the next moment it's compacted wreckage. The pressure sees any weakness and exploits it instantly. This is why deep-sea submersibles are pressure-sealed. The interior is kept at normal atmospheric pressure. The hull holds back the ocean, bearing all that force so the people inside can breathe normally. The submersible's hull might be titanium or steel, several inches thick, carefully designed with spherical or cylindrical shapes to distribute the pressure evenly. Even then, the submersible shrinks slightly under the pressure. When James Cameron descended to Challenger Deep in 2012, his submersible, Deep Sea Challenger, compressed by approximately 3 inches. 3 inches out of a vehicle that stood roughly 24 feet tall. The entire structure squeezed inward by the pressure. This compression is elastic. When the submersible ascends and the pressure releases, it expands back to normal size. But during the dive, every part of the structure is under immense stress. The materials are being tested at their limits. Any flaw, any weakness in the design or construction, any tiny crack or imperfection could be catastrophic. One failure and the pressure would rush in. Water would compress the air inside to nothing in a fraction of a second. Everything inside would be destroyed instantly. The pressure doesn't just affect air and foam, it affects water itself. This seems counterintuitive. Water is incompressible, right? That's what we're taught. Liquids don't compress. Except that's not quite true. Water does compress under pressure, just very slightly. At Challenger Deep, the pressure is so great that water becomes roughly 5% denser than at the surface. 5% might not sound like much, but it means that water at the bottom of the ocean is heavier, more compact than water at the top. This has implications for ocean, circulation, for how water masses move and mix. Dense water sinks, less dense water rises. The pressure-induced density change at great depths affects these processes in subtle but important ways. Water's compressibility also affects sound. Sound travels faster in denser water. At Challenger Deep, sound moves roughly 3% faster than at the surface. This matters for sonar, for underwater communication, for how we map the ocean floor. We have to account for the way pressure changes water's properties when we interpret our measurements. But perhaps most remarkable is what pressure does to living things, or rather, what it doesn't do to some living things. Because despite the crushing force at the bottom of the ocean, life exists there, thrives there. When Jacques Piccard and Don Walsh made the first descent to Challenger Deep in 1960 aboard the bathyscaphe Trieste, they reported seeing a flatfish on the bottom. Scientists were skeptical. At that pressure, calcium can't remain solid. It dissolves. Bones should dissolve. Fish have bones. How could a fish exist where bones can't exist? Some scientists suggested Piccard saw a sea cucumber, not a fish. Others argued about what fish-like even means at those depths. The debate continues. But one thing is certain, life exists at Challenger Deep. We've seen it. Amphipods, shrimp-like crustaceans. We've found them in the deepest trenches. We've captured them, brought them up, studied them. These creatures have adapted to pressure in ways that seem almost impossible. Their bodies contain no air spaces, no swim bladders like shallow water fish use for buoyancy, no air pockets anywhere. Their cells are filled with incompressible fluids. The pressure outside equals the pressure inside. They're in equilibrium with their environment. Their proteins are different too. Normal proteins denature under high pressure. The molecular structures change. The proteins stop working. But deep-sea organisms have evolved proteins with special adaptations, different amino acid sequences that remain stable under pressure, molecules called piezolites that counteract pressure's effects. These adaptations allow their cellular machinery to function where ours would fail instantly. And here's what's truly mind-bending. These creatures are adapted to high pressure. Some of them require it. Bring them up to the surface and they die. Not from decompression in the way a scuba diver might get the bends. These organisms don't breathe air, so they don't have nitrogen bubbles forming in their tissues. They die because their proteins don't work at low pressure. Their cellular processes fail. The very things that adapted them to the deep make them unable to survive anywhere else. They're as trapped in the deep ocean as we're trapped at the surface. We can visit their world briefly. in protective vehicles, but we can never live there, and they can never live here. The pressure barrier is absolute. This gets to the heart of why. We cannot replicate deep ocean conditions. It's not just about building a strong chamber, it's about creating an environment, an ecosystem. The deep ocean is a place where pressure defines every aspect of existence, where evolutionary adaptations span millions of years, where physical and chemical processes operate under conditions foreign to surface life. You can put an amphipod in a pressure chamber and keep it alive. Scientists have done this. But you're not recreating the deep ocean, you're just applying pressure. The temperature is wrong, the water chemistry is wrong, the food sources are absent, the biological community is missing, the chamber is too small for the organism to behave naturally. It's a test environment, not a habitat. The ocean creates pressure through volume, through sheer scale. Cubic kilometre upon cubic kilometre of water stacked up, layer upon layer, the weight accumulating until it reaches magnitudes we can barely engineer. We can create pressure in a chamber by pumping in compressed gas or fluid, but it's not the same. The mechanism is different, the scale is different, and most fundamentally, the purpose is different. The ocean's pressure isn't trying to be high pressure, it just is. It's an emergent property of having that much water in one place, under gravity's influence. Our pressure chambers are designed, constructed, maintained systems fighting against the natural tendency of pressurized fluids to expand. We're containing something that wants to escape. The ocean is just being the ocean. So why does this matter? Why does it matter that we cannot replicate ocean pressure at scale? Because it limits our understanding. It limits our ability to study deep-sea life, to test equipment properly, to prepare for the challenges of ocean exploration. When engineers design a submersible or an underwater research station, or a deep-sea mining robot, they need to test it. They need to verify that the seals will hold, that the hull won't crack, that the systems will function under pressure. Right now, we can test components, individual parts, but we cannot test the entire system in realistic conditions. The pressure chambers aren't big enough, so instead, we test what we can and extrapolate. We use computer simulations to predict how the full system will behave. We build in safety margins, redundancies, backups, and then we deploy it in the real ocean and hope our predictions were correct. Sometimes they are, sometimes they're not. In 2009, the remotely operated vehicle Nereus descended to Challenger Deep. It was a hybrid vehicle, capable of operating both tethered and autonomously. 4 years later, in 2014, while diving at nearly 10,000 meters in the Kermadec Trench, Nereus imploded. The pressure crushed it. Something failed. We don't know exactly what because the vehicle was destroyed. The wreckage was recovered, but the pieces were too damaged to determine the exact failure point. Years of development, millions of dollars, groundbreaking science, all lost because something couldn't handle the pressure. This is the risk of deep ocean work. You cannot fully test your equipment before deployment. You cannot perfectly predict how materials will behave over time under such extreme stress. Fatigue failures develop. Tiny cracks propagate. Seals degrade. And when something fails at full ocean depth, it usually fails catastrophically. The pressure differential is too great for gradual leaks. Either the seal holds or it doesn't. Either the hull withstands the force or it collapses. There's no middle ground. The ocean is unforgiving at those depths. Think about the Titan submersible disaster in 2023. A privately built submersible descending to view the Titanic wreck at about 3,800 meters depth. The submersible imploded, killing all 5 people aboard. Investigations suggested the carbon fiber hull had degraded over multiple dives. Tiny delaminations, small flaws that accumulated over time. Each dive cycle stressed the material. Each return to the surface allowed it to expand. Compress, expand, compress, expand. Eventually, the material couldn't take it anymore. It failed. The pressure rushed in. Everyone died instantly. This tragedy happened at depths we consider relatively accessible. 3,800 meters is the average ocean depth. Terrible pressure by human standards, but nowhere near the deepest parts. The Challenger. Deep is nearly 3 times deeper. The pressure there is nearly 3 times greater. The engineering challenges scale exponentially. And yet, people have been there, successfully. The key difference is approach. The submersibles that work at full ocean depth are built with enormous safety margins, conservative designs, proven materials, extensive testing of every component. The Trieste had a steel sphere for the crew, designed to withstand far more than the expected pressure. James Cameron's deep-sea Challenger used a pilot sphere made of specialized syntactic foam, incredibly strong and precisely engineered. Victor Vescovo's limiting factor submersible, which has now made multiple descents to Challenger Deep, uses a titanium pressure sphere designed and built by Triton submarines with meticulous attention to detail. These vehicles cost tens of millions of dollars. They represent years of engineering work. They undergo exhaustive component testing, and even then, even with all that preparation, there's risk. There's always risk when you cannot fully replicate the environment you're designing for. Let's think about this from a different angle. Let's think about energy. Creating high pressure requires energy. In a pressure chamber, you're doing work against the natural tendency of gases and fluids to expand. You're compressing them, forcing molecules closer together than they want to be. This requires pumps, compressors, power. To reach 1,000 atmospheres in a chamber, you need robust high-pressure pumps running continuously. The system must maintain that pressure. Any leak, any failure, and the pressure drops. The energy input must be constant. In the ocean, gravity does the work. The water is already there. It's already stacked up miles high. Gravity pulls it down. That's it. No pumps needed. No power required. The pressure exists passively, constantly, for free. This is an important distinction. We can create high pressure, but we cannot create it easily or cheaply at large scales. The energy cost is prohibitive. If you wanted to build a pressure chamber big enough to hold a person at Challenger deep pressure, you'd need to pump an enormous volume of fluid to extremely high pressure. The pump would need to be massive, the power requirements would be substantial, the infrastructure would be complicated and expensive, and you'd need to keep it all running safely. One mistake, one equipment failure, one power outage, and the pressure drops. Or worse, something fails catastrophically. The ocean requires none of this infrastructure. It's self-sustaining. The pressure is stable. It doesn't require monitoring or maintenance. It just exists. This is why the ocean is the only place to truly experience full ocean depth pressure. You cannot recreate it on land. Not at scale. Not practically. The engineering required is beyond what makes sense economically or practically. We can simulate it for small test objects, but that's fundamentally different from replicating the environment. There's another factor we haven't discussed yet: temperature. The deep ocean is cold. At Challenger Deep, the temperature hovers between 1 and 4 degrees Celsius, just above freezing. This cold temperature affects how materials behave under pressure. Metals become more brittle when cold. Seals might stiffen or crack. Lubricants thicken. Chemical reactions slow down. The combination of extreme pressure and near-freezing temperature creates a unique environment. You can't just test something under pressure at room temperature and assume it will work the same way in the cold deep ocean. You need to test under pressure and cold simultaneously. This adds complexity. Most pressure chambers operate at room temperature or higher. Creating a chamber that's both high pressure and cold requires additional engineering. You need refrigeration systems that can work under pressure, thermal insulation that can withstand pressure, materials that remain functional in both conditions. Again, we can do this for small chambers, but scaling it up becomes increasingly difficult. Add in the corrosive nature of seawater, which we haven't even discussed yet, and the challenges multiply further. Seawater is corrosive. Salt accelerates corrosion of metals. Long-term exposure requires special materials or protective coatings. You can test corrosion separately, you can test pressure separately, you can test cold separately, but testing all three simultaneously at full ocean depth conditions in a chamber large enough to be meaningful is extraordinarily difficult. The ocean does all of this naturally. Pressure, cold, corrosion, all at once, in volumes that dwarf anything we can build. And it does it for free. No power required, no maintenance. It's just the state of that environment. This is what makes ocean pressure unique. It's not just about the numbers, it's about the totality of the environment. Let me take you back to those early days of deep ocean exploration. Before we had sophisticated submersibles or remotely operated vehicles, when humans first started thinking about going deep. The bathyscaphe Trieste was built in the 1950s by Auguste Piccard and his son Jacques. The design was clever, a large float filled with gasoline for buoyancy, and underneath, a steel sphere for the crew. Gasoline is less dense than water, so it floats. But unlike air, gasoline is nearly incompressible. It doesn't crush under pressure the way air would. The float provided buoyancy without requiring a pressure-resistant structure. All the pressure resistance was concentrated in the cryosphere. On January 23, 1960, Jacques Picard and Don Walsh climbed into that sphere and began descending into the Mariana Trench. The descent took almost 5 hours. 5 hours of sinking slowly through total darkness, watching the depth gauge climb higher and higher. The pressure increased steadily. At around 9,000 meters, they heard a loud crack. Something had broken. They debated whether to abort, but the instruments showed the sphere was intact. They decided to continue. Later, they discovered that an exterior window on the entrance tunnel had cracked. Not the main viewing window, thankfully, just a small window in a less critical area. They reached the bottom at 10,916 meters, though later measurements suggest they were probably closer to 10,900 meters. The pressure at that depth was approximately 1,085 times atmospheric pressure, over 8 tons per square inch pressing on every surface of the sphere. They spent about 20 minutes on the bottom, 20 minutes in a place no human had ever been. They looked out the small viewing port and reported seeing that controversial flatfish. They took notes, they made observations, and then they began the ascent, 3 hours and 15 minutes to return to the surface. When they emerged, they'd proven that humans could reach the deepest part of the ocean. But here's what's telling. After the Trieste's dive, no one returned to Challenger Deep for 52 years. 52 years. Why? Because it's incredibly difficult, incredibly expensive, incredibly dangerous. The technology to go there exists, but it's not easy technology. It's not routine. Every dive requires meticulous planning, extensive preparation, enormous resources. James Cameron's dive in 2012 brought new attention to the deep ocean. His submersible Deep-Sea Challenger was purpose-built for the mission, vertical rather than horizontal in design. A pilot sphere at the bottom, batteries and systems stacked above. The whole vehicle was like a tall, thin torpedo designed to descend and ascend efficiently. Cameron spent hours at the bottom. He collected samples. He filmed in high definition. He brought back science and imagery that helped us understand the deepest ocean better. But again, this was a one-time mission. The submersible made one successful dive to Challenger Deep. It was designed for more, but circumstances prevented additional dives. The vehicle is now in a museum. Since then, only one submersible has made repeated trips to full ocean depth. Victor Vescovo's limiting factor. This submersible, built by Triton Submarines, has descended to the deepest points in all 5 oceans, multiple dives to Challenger Deep, multiple explorers taken to the bottom. It's arguably the most successful deep ocean vehicle ever built. But even limiting factor is small. It carries 1 or 2 people. The pressure sphere is cramped. The dive time is limited by life support and battery capacity. You can reach the bottom, but you cannot stay long. You cannot live there. These submersibles prove we can visit extreme depths. But visit is the key word. We're tourists, brief visitors to an environment that remains fundamentally hostile to human life. We've developed the technology to peek into the abyss, but we haven't mastered it. We haven't made it routine. We haven't made it safe enough or cheap enough or easy enough for regular access. And a big part of why is because we cannot adequately test and prepare on land. We cannot build pressure chambers that replicate the conditions. We have to test components, trust our engineering, and accept the risks. Now, I want to talk about something that might seem tangential, but is actually central to understanding why ocean pressure is so special. I want to talk about the sheer volume of the deep ocean. The Pacific Ocean alone contains roughly 715 million cubic kilometers of water. 715 million. That's a number so large it's almost meaningless. Let me try to put it in perspective. If you took all the land on Earth, all the continents, all the islands, and stacked them up, you'd need to stack them roughly 11 times over to equal the volume of the Pacific Ocean. All the water in all the lakes, all the rivers, all the groundwater, all the ice caps, all combined, that's about 2.5% of the ocean's volume. The ocean is 97.5% of Earth's water, and most of that ocean is deep. The average depth is 3,800 meters. There are vast areas deeper than 6,000 meters. The Hadal Zone, the deepest parts, the ocean trenches, these represent a small percentage of the ocean floor, but still contain enormous volumes of water. The volume of Water deeper than 6,000 meters is estimated at around 45 million cubic kilometers. That's just the deepest parts. That's more water than exists in all the rivers and lakes on Earth combined, all compressed into the narrow trenches that cut into the ocean floor. And every single cubic meter of that water contributes to the pressure. Consider the Mariana Trench itself. It's roughly 2,550 kilometers long and 69 kilometers wide on average. The deepest parts form a crescent-shaped gash in the ocean floor. If you could somehow remove all the water from the trench, you'd have a chasm that would dwarf the Grand Canyon. Mount Everest, Earth's tallest mountain at 8,848 meters, could fit inside the Mariana Trench with over 2 kilometers of space above it. 2 kilometers. That's another 6,000 feet of depth beyond Everest's summit. The scale is difficult to comprehend. Now, consider what this means for pressure. Every cubic meter of seawater weighs roughly 1,000 kilograms, a metric ton. At the average ocean depth of 3,800 meters, there's 3,800 meters of water above any point on the floor. That's 3,800 tons of water in a column 1 square meter in area. Multiply that by the roughly 361 million square kilometers of ocean floor, and you get an incomprehensible amount of weight. This weight creates pressure everywhere in the deep ocean simultaneously. It's not like we're talking about one point where pressure exists. Pressure exists across millions of square kilometers of ocean floor, continuously, constantly, day and night, year after year, millennium after millennium. The pressure has existed for as long as the ocean has been roughly this deep, hundreds of millions of years. You cannot replicate this with a pressure chamber. You can create pressure at a point, in a small volume, for a limited time, but you cannot create the spatial extent. The ocean's pressure field spans the globe. It's three-dimensional. It affects everything in the water column from the surface down. It shapes how water moves, how heat distributes, how chemicals dissolve and precipitate. It's not just a force. It's a defining characteristic of the entire marine environment. And here's something else. The pressure is stable. It doesn't fluctuate. The ocean's depth doesn't change significantly. Tides cause water level variations of a few meters, but at depths of thousands of meters, this is negligible. The pressure at Challenger Deep today is the same as it was yesterday, the same as it will be tomorrow. This stability has allowed life to adapt to specific pressure conditions. Deep-sea organisms are tuned to their depth range. They've evolved over millions of years in an environment where pressure is constant. They don't experience pressure changes in their normal lives. If you built a pressure chamber to house deep-sea organisms, you'd need to maintain constant pressure. Any fluctuation would stress the organisms, and maintaining constant pressure in a mechanical system is harder than it sounds. Pumps cycle. Pressure regulators respond to changes. Temperature variations affect pressure. In the ocean, the pressure is constant because it's not being maintained by machinery. It's a natural consequence of depth. The water is always there. Gravity is always acting on it. The pressure is self-regulating. This is an impossible standard to meet artificially. We can approximate it. We can build systems that maintain relatively stable pressure, but matching the ocean's natural stability over long time periods in large volumes is beyond our current capabilities. Let's shift to thinking about pressure from a more philosophical angle. What does it mean that we cannot replicate this force? What does it say about our relationship with the ocean? Humans have conquered many environments. We've climbed the highest mountains. We've crossed the hottest deserts. We've survived in the coldest regions of Antarctica. We've sent people to space, where there's no air and the temperature swings between extremes. We've adapted. We've built technology to protect us. We've made the hostile survivable, if not comfortable. But the deep ocean remains fundamentally beyond us. We can visit briefly, in tiny protected capsules, but we cannot stay. We cannot build habitats there. We cannot live there. The pressure makes it impossible. Unlike space, where the challenge is lack of pressure, and we can build pressurized habitats, the deep ocean has too much pressure pressing inward. We cannot build structures large enough to house people that can resist those forces. Submarines exist, but they're small, cramped, limited in duration. There's no deep ocean equivalent of the International Space Station, no underwater research base at full ocean depth. Consider what we've achieved in space. The International Space Station has been continuously occupied since the year 2000. 25 years of constant human presence in orbit. Astronauts live there for months at a time. They conduct experiments. They maintain the station. They've adapted to microgravity. The station is large, multiple modules connected together, room to move around, places to sleep, eat, work, exercise. Yes, it's cramped by Earth standards, but it's a functional long-term habitat, and it exists in an environment just as hostile as the deep ocean in many ways. The vacuum of space would kill you instantly without protection. Radiation bombards everything. Temperature swings are extreme. Micrometeoroids pose constant risk, yet we've made it work. We've built a place where people can live, at least temporarily. Why can't we do the same in the deep ocean? The answer is pressure. In space, the challenge is containing 1 atmosphere of pressure inside the station while there's vacuum outside. The pressure differential is 1 atmosphere. The walls of the ISS don't need to be particularly thick. They're designed more for micrometeorite protection and thermal control than pressure containment. 1 atmosphere pushing outward isn't that difficult to manage. In the deep ocean, you'd be trying to maintain 1 atmosphere inside while over 1,000 atmospheres press from outside. The pressure differential is 1,000 times greater. The structural requirements increase exponentially. You'd need walls so thick, material so strong, design so robust that the structure might not be buildable with current technology. And even if you built it, deploying it to the ocean floor would be enormously challenging. How do you sink something that massive without damaging it? How do you position it precisely? How do you anchor it against ocean currents? The logistics are daunting. Then there's maintenance. On the ISS, when something needs repair, astronauts can spacewalk outside. They wear spacesuits pressurized to a fraction of an atmosphere and work on the exterior. In the deep ocean, stepping outside isn't possible. You cannot build a suit that would let you survive at Challenger deep pressure. The best atmospheric diving suits, which maintain 1 atmosphere around the diver, are rated to around 600 meters depth, 60 atmospheres, nowhere near deep ocean depths. At Challenger Deep, you'd need to send remotely operated vehicles to do any exterior work, or build everything so it never needs maintenance, which is essentially impossible for long-term operations. The deepest underwater habitats ever built operated at relatively shallow depths. Aquarius Reef Base, still operational, sits at about 20 meters depth. Conshelf experiments in the 1960s reached 100 meters. But that's nowhere near the deep ocean. Those are shallow water habitats by comparison. The engineering required to build a habitat at even 1,000 meters depth would be extraordinary. At full ocean depth, it's not just extraordinary, it's essentially impossible with current technology. The pressure vessel would need to be so thick, so heavy, so robust, that transporting it and deploying it would be nearly impossible, and maintaining it would be even harder. Any malfunction, any failure would be catastrophic. This represents a limit to human expansion. We talk about colonizing other planets, living on Mars or the Moon. Those seem more achievable than colonizing the deep ocean on our own planet. The pressure barrier is that formidable. It's a humbling realization. There's a place on Earth, covering most of Earth's surface, that we fundamentally cannot occupy. We've developed amazing technology. We've split the atom, decoded DNA, built computers that fit in our pockets and connect us globally. We can cure diseases that would have killed us a century ago. We can see distant galaxies and detect gravitational waves. We can do remarkable things, but we cannot live in the deep ocean. The pressure is too great, and we cannot recreate that pressure at scale on land to practice, to prepare, to truly understand what we're dealing with. This isn't a failure of human ingenuity. It's a recognition of physical limits. Some environments are fundamentally incompatible with human biology and current technology. The deep ocean is one of them, not because we haven't tried hard enough or been clever enough, because the physics are unforgiving. So what do? We work within our limits. We build the best submersibles we can. We test components in the pressure chambers we have. We use computer simulations and materials science to predict behavior. We proceed carefully, accepting risk when we must, and we send robots instead of people when possible. Remotely operated vehicles and autonomous underwater vehicles can go places humans cannot. They don't need life support. They don't need large pressure spheres. They can be built more compactly, but even robots fail under pressure. Even the best engineered systems have limits. The deep ocean has destroyed many ROVs and AUVs over the years, crushed them, flooded them, rendered them inoperable. Each failure teaches us something. Each success builds confidence. Slowly, incrementally, we're getting better at working in these environments, but we're not mastering them. We're accommodating them, learning to operate within their constraints. The pressure remains the dominant factor. It shapes what's possible and what's not. And we cannot change it. We cannot reduce it. We cannot escape it when we're down there. Let me tell you about some of the organisms that live under this pressure, because they represent one of the most remarkable examples of adaptation in nature. Take the snailfish. Several species of snailfish live at extreme depths. In 2017, researchers recorded a snailfish at 8,134 meters in the Mariana Trench, the deepest fish ever recorded. This fish is living under pressure roughly 800 times atmospheric pressure. Its body contains no air spaces, it has no swim bladder, its bones are thin and flexible, not rigid like ours. It's mostly soft tissue and fluid. The fish is essentially pressure neutral. The pressure inside equals the pressure outside. But this creates a problem. Normal fish enzymes and proteins don't function at high pressure. The molecular structures change shape, enzymatic reactions stop working, the cell membranes become too rigid, life should be impossible. And yet, the snailfish lives. How? Researchers have found that deep-sea fish have evolved special proteins. Their enzymes have different amino acid sequences that remain functional under pressure. They produce molecules called TMAO, trimethylamine N-oxide, in high concentrations. TMAO is an organic osmolyte. It counteracts the effects of pressure on proteins. It helps maintain the right protein structure, even when the pressure is trying to compress and deform molecular shapes. The deeper the fish lives, the more TMAO it produces. This is a direct evolutionary response to pressure. The fish has biochemically adapted to an environment that would kill us instantly, but there's a limit. As you go deeper, fish need more and more TMAO to counteract pressure. Eventually you need so much TMAO that it becomes toxic. The fish can't produce enough to survive. This appears to be around 8,000 to 8,500 meters. Below that depth, we don't find fish. We find invertebrates, amphipods, isopods, sea cucumbers. These organisms have different body plans, different biochemistries. They can survive deeper than fish, but they're also adapted specifically to pressure. The amphipods found in the deepest trenches are remarkable creatures. They're small, typically just a few centimeters long, but they're found in astonishing abundance. When baited traps are lowered to challenge a deep, they sometimes return with hundreds or thousands of amphipods swarming over the bait. These creatures are scavengers, feeding on whatever organic matter falls from above. They have hard exoskeletons made of chitin, like all crustaceans, but their shells are slightly flexible to accommodate the pressure. Inside, their bodies are filled with lipids and proteins specially adapted to high pressure. Scientists have studied these amphipods and found remarkable biochemical adaptations. Their cell membranes have different compositions than surface organisms. The ratio of saturated to unsaturated fatty acids is adjusted to keep membranes fluid under pressure. Their DNA repair mechanisms are enhanced because pressure can damage DNA over time. Their metabolic pathways are modified to function efficiently in this extreme environment. And here's something fascinating. Some of these adaptations appear to be universal across deep-sea organisms from different lineages. Organisms that evolved separately, descended from different ancestors, have independently arrived at similar solutions to the pressure problem. This is convergent evolution driven by the relentless selective pressure of the environment. The deep ocean pressures life into certain biochemical solutions, and those organisms that find those solutions survive. Those that don't, perish. Bring them to the surface and most die. Not from decompression sickness like a diver would experience. They die because their proteins stop working at low pressure. Their cellular machinery fails. They're adapted to high pressure to such a degree that low pressure is lethal. Think about the implications. These organisms cannot be studied easily in normal laboratories. You'd need to maintain them at high pressure constantly. You'd need pressure aquariums, pressure feeding systems, pressure observation chambers. The equipment exists for short-term studies, but long-term maintenance of deep-sea organisms at their native pressure is extremely difficult. Most die within hours or days when brought to surface laboratories, even if kept cold and in seawater. The pressure change is too much, so our ability to study deep-sea life is limited by our inability to replicate their environment. We can observe them briefly during submersible dives. We can collect specimens and study them immediately on the ship in specialized high-pressure containers. But we cannot keep them alive long-term. We cannot observe their full life cycles. We cannot study their behavior in natural conditions. The pressure barrier prevents it. This is a significant limitation for marine biology. There are likely thousands of species in the deep ocean we haven't discovered yet, behaviors we haven't observed, ecological relationships we don't understand, and we're handicapped in our ability to study them because we cannot recreate their environment on land. Every discovery requires an expensive deep-sea expedition. Every observation requires sophisticated equipment deployed at great cost and risk. Now, let's consider pressure's role in Earth's larger systems, because this is where things get really interesting. Pressure affects water density. Dense water sinks, less dense water rises. This drives ocean circulation. The ocean has currents, not just surface currents driven by wind, but deep currents driven by density differences. Cold water is denser than warm water, salty water is denser than fresh water, and pressure makes deep water slightly denser than surface water. This sets up a global circulation pattern called the thermohaline circulation. Water cools at the poles, becomes dense, and sinks. It flows along the ocean floor toward the equator. Eventually it rises and warms and returns to the poles at the surface. This cycle takes hundreds of years to complete. It's one of the major ways Earth redistributes heat from the equator to the poles. It affects climate, it affects weather patterns. It's fundamental to how our planet regulates temperature, and pressure plays a role in this. Not the dominant role. Temperature and salinity are more important, but pressure's effect on density matters. It contributes to the stratification of the ocean. Deep water is denser partly because it's under pressure. This stabilizes the water column in some ways, makes mixing harder, affects how nutrients and dissolved gases distribute vertically. The deep ocean acts as a massive reservoir of cold, dense water. This water can remain at depth for centuries before rising back to the surface. While it's down there, it's under enormous pressure. That pressure affects its physical properties, its density, its compressibility, even its ability to hold dissolved gases. Scientists who study ocean circulation must account for pressure when modelling how water moves through the deep ocean. The equations that govern fluid flow include pressure terms. The way water parcels move depends partly on pressure gradients. Areas of higher pressure push water toward areas of lower pressure. This creates flow. At the scale of the global ocean, these pressure gradients are small, tiny differences in pressure across vast distances, but they add up. They drive circulation patterns that span ocean basins, that connect the Atlantic to the Pacific to the Indian Ocean, that move heat and salt and carbon around the planet. Understanding these processes requires understanding pressure, not just the absolute pressure at a given depth, but how pressure varies horizontally and vertically, how it changes with temperature and salinity, how it interacts with Earth's rotation to create complex three-dimensional flow patterns. Pressure also affects chemical reactions. Some reactions proceed differently at high pressure than at low pressure. Minerals that are stable at the surface might dissolve at depth. Minerals that dissolve at the surface might precipitate at depth. This affects the chemistry of seawater. It affects how carbon cycles through the ocean. Carbon dioxide dissolves in seawater. Under pressure, more CO2 can dissolve. The deep ocean acts as a carbon sink, absorbing CO2 from the atmosphere. The pressure at depth helps keep that carbon dissolved. If you brought deep water to the surface quickly, some of that dissolved CO2 would come out of solution, like opening a carbonated beverage. The pressure release allows gas to escape. This has implications for ocean acidification, for climate change, for understanding how the ocean and atmosphere exchange carbon. And we cannot easily study these processes in the laboratory. You can pressurize a water sample and measure how much CO2 dissolves. But replicating the full complexity of ocean chemistry under realistic pressure conditions, with all the other dissolved substances present, with biological processes occurring, is enormously difficult. The ocean is a complex chemical system. Pressure is one of many variables. To understand it fully, you need to study it in situ, in the actual ocean, at actual depth. Pressure also affects geological processes. At mid-ocean ridges, magma rises from the mantle and creates new ocean floor. The pressure at these depths affects how the magma behaves, how gases dissolve in the magma, how minerals crystallize. Underwater volcanoes operate under pressure that would be impossible to replicate in a laboratory. The lava that erupts underwater behaves differently than lava on land because of the pressure. It forms pillow structures, bulbous shapes created as the outer surface rapidly cools in contact with water, while the interior stays molten and pressure pushes it outward. You can try to recreate this in experiments. You can pressurize a chamber and extrude hot material into water. But it's not the same as a real underwater eruption. The scale is different. The pressure gradients are different. The thermal dynamics are different. Again, we come back to the limitation. We can approximate, we can model, but we cannot replicate. The ocean creates these conditions naturally. We struggle to match them artificially. And now let's talk about the human side of all this, about what it's like to actually descend into the deep ocean, knowing the pressure outside. I've never done it myself, but I've read accounts from those who have. The experience is apparently surreal. You climb into a tiny sphere, maybe 6 feet in diameter, just enough room to sit. You're sealed inside. The hatch is closed, bolted shut. You're committed now. The submersible is lowered into the water. You begin to sink. At first there's light. The water is blue. You can see the surface above, the sunlight filtering through. Then you pass through what's called the euphotic zone, where enough light penetrates for photosynthesis. The water darkens. Blue becomes deep blue, becomes black. By 200 meters, it's dark. By 1,000 meters, it's absolute blackness. The only light is from the submersible's own lights, and you keep descending. The depth gauge counts upward. 1,000 meters, 2,000, 3,000. You're falling through darkness. The temperature outside drops close to freezing. The pressure builds. 500 atmospheres, 600, 700. You know intellectually that the hull is designed for this, tested, built with safety margins, but you also know that you're in an environment completely hostile to human life. The pressure outside could crush you like an insect if the hull failed. You're entirely dependent on the engineering, on the materials, on the seals, on everything working exactly as designed. At Challenger Deep, the descent takes hours, 3 to 5 hours of sinking through darkness, waiting, watching instruments. The pressure builds to over 1,000 atmospheres, over 8 tons per square inch. You can hear the hull creaking, materials adjusting to stress. It's unnerving. You trust the engineering, but the sounds remind you of the forces at work. When you reach the bottom, you're nearly 11 kilometers below the surface, 11 kilometers of water above you, the weight of an entire ocean pressing down. You look out the viewport and see mud, the ocean floor, maybe some organisms, amphipods, sea cucumbers. You've made it. But you're acutely aware that you're in a place humans do not belong. You're a visitor in a metal sphere. The only thing between you and instant death is a few inches of titanium or steel. You stay for hours if you can, collecting samples, taking video, making observations, but you cannot forget the pressure. It's always there, always pressing. When it's time to ascend, you drop weights. The submersible becomes buoyant and begins to rise. 3 to 4 hours to return to the surface. The pressure gradually decreases. The depth gauge counts down. Eventually you see light. The surface. The hatch opens. You're back in the normal world. Back where humans belong. The experience changes people. Many describe it as humbling, awe-inspiring, terrifying and beautiful. You've been to a place almost no one has been. You've seen things few have seen. And you've felt the weight of the entire ocean. The pressure. Even though you were protected from it, you knew it was there. You respected it. Because if you don't respect it, it will kill you. Let's talk about the future. Where do we go from here? How do we advance deep ocean science when we cannot replicate the environment we're trying to study? The answer is better technology for in situ research. More sophisticated ROVs and AUVs that can operate at full ocean depth. Longer duration missions, better sensors, better imaging systems. The ROVs of today are far more capable than those of 20 years ago. They have high-definition cameras, manipulator arms that can collect samples delicately, sensors that measure temperature, salinity, chemical composition. They can stay down for hours or days tethered to a ship above. Autonomous vehicles are getting better too. They can map the ocean floor, follow programmed routes, collect data and return to the surface. But there are limits. Power is one. Batteries only last so long at depth. The cold reduces battery efficiency. Long missions require large battery packs, which add weight, which requires more buoyancy. Communication is another limit. Radio waves don't travel through water. You can't use Wi-Fi or GPS underwater. Acoustic communication works but has limited bandwidth and range. If an AUV is out of acoustic range, you cannot talk to it. It's on its own. This makes long, autonomous missions risky. If something goes wrong, the vehicle might be lost, and deep ocean AUVs are expensive. Losing one is costly. The ocean's pressure contributes to these challenges. High-pressure electronics are difficult to design. Every connection, every seal is a potential failure point. Batteries must be pressure compensated or housed in pressure vessels. Cameras need pressure-resistant windows. Every component must be rated for depth. This adds complexity and cost, but progress continues. Engineers are developing better materials, better sealing technologies, more efficient power systems. Each generation of deep ocean vehicles is more capable than the last. We're also getting better at using what we learn from each deployment. Every dive generates data. Every failure teaches us something. We're building institutional knowledge. Slowly, we're improving our ability to work at depth. But we're still limited by our inability to test systems fully before deployment. We cannot build a pressure chamber large enough to test a full-size ROV at Challenger deep pressure. We test components, assemble the vehicle, and hope it works. Often it does, sometimes it doesn't. There's talk of building larger test facilities, deeper rated pressure chambers, more sophisticated simulation capabilities. These would help. But the fundamental constraint remains. To truly replicate Challenger deep pressure in a chamber large enough to be useful would require engineering on a scale we haven't attempted. It might not even be economically feasible. The ocean will likely remain the only place to truly test deep ocean equipment, which means every deployment carries risk. Every mission is partly experimental. This is the reality of deep ocean research. We work with partial information, we do our best engineering, we build in safety margins, and we accept that sometimes things will fail. The pressure is too great, the environment too extreme, mistakes are unforgiving. But the potential discoveries drive us forward. The deep ocean is Earth's last great frontier. We've explored less of it than we've explored the surface of the Moon or Mars. There are species there we've never seen, geological features we don't fully understand, chemical and biological processes that might reveal new principles. The pressure is a barrier, but it's also what makes the deep ocean unique. It creates an environment unlike anywhere else on Earth, an environment that has driven evolution in fascinating directions. Understanding that environment, learning to work within it, is one of the great challenges of marine science, and we cannot do it from the comfort of a laboratory. We have to go there. So here we are, at the end of this exploration. We've talked about what hydrostatic pressure is, how it forms, what it does to materials and living things. We've discussed why we cannot replicate it at scale, why the ocean remains the only place where full ocean depth pressure exists in volumes large enough to matter. We've looked at the engineering challenges, the biological adaptations, the human experience of descending into the abyss. And the central truth is this: the ocean creates conditions we cannot match. Not because we lack the knowledge or the ingenuity, but because the ocean operates at a scale that defies our technology. It's too big, too deep, too massive. The weight of all that water creates pressure through a mechanism so simple and so enormous that our pressure vessels cannot compete. We can approximate it for small objects, but we cannot replicate the environment. We cannot build chambers where people could experience Challenger deep pressure and survive. We cannot create the spatial extent, the stability, the naturalness of ocean pressure. It's a humbling realization. In an age where we can do so many remarkable things, where technology seems to advance almost daily, where we talk casually about colonizing other planets, the deep ocean on our own world remains largely beyond our reach. Not completely. We can visit, we can study, we can learn, but we cannot occupy. We cannot make it routine. The pressure sees to that. Think about what this means for the future of ocean science. Every major advance in our understanding of the deep sea has required going there, actually deploying equipment to depth, actually taking the risks. We cannot simply build better laboratories on land and unlock the ocean's secrets. The ocean must be studied in the ocean. This is fundamentally different from many other scientific fields. If you want to study particle physics, you build an accelerator. If you want to study materials science, you build a laboratory with the tools you need. The environment comes to you, you control it. You recreate the conditions you want to study. But if you want to study the deep ocean, you must go there. You must accept the environment on its terms. You must work within constraints you cannot change. The ocean dictates the rules, and those rules are harsh, unforgiving. The pressure is just one of many challenges. The cold, the darkness, the distance from the surface, the corrosive seawater, the lack of GPS or reliable communication. All of these factors combine to make deep ocean research extraordinarily difficult, and pressure underpins all of it. Pressure determines what equipment can survive, how long missions can last, what risks are acceptable. The pressure is always there, always pressing, always waiting for any weakness to exploit. Despite these challenges, we keep going back. We keep building better submersibles, better ROVs, better sensors and cameras and sampling equipment. We keep pushing the boundaries of what's possible, because the deep ocean holds answers we need. It's Earth's largest habitat. It plays crucial roles in climate regulation, nutrient cycling, carbon sequestration. It hosts ecosystems we're only beginning to understand, species we haven't discovered, processes we haven't documented. Ignoring it isn't an option. Understanding it is essential, but understanding it requires accepting that we're working at the edge of human capability, in an environment we cannot fully replicate or control, where nature holds all the advantages and we're merely visitors, tolerated briefly by an environment that could destroy our equipment, and us, in an instant if given the chance. And perhaps that's okay. Perhaps it's good that there are places on Earth that remind us of our limits, that humble us, that force us to respect the natural world rather than assume we can control it. The deep ocean is one of those places. The pressure there is a force we cannot replicate, a force that shapes everything about that environment, a force that will likely remain unique to the ocean for the foreseeable future. There's something profound about this. We live in an era of unprecedented technological capability. We can edit genes with precision. We can see individual atoms with electron microscopes. We can send spacecraft to the outer solar system and land them on comets. We can detect gravitational waves from colliding black holes billions of light years away. We have achieved things that would seem like magic to people living just a century ago. And yet, a simple column of water stacked high enough creates a force we cannot match. Not with our most advanced engineering, not with our most sophisticated materials, not with unlimited budgets. The ocean does it effortlessly, naturally, just by existing. This should give us pause. It should make us think carefully about our relationship with the ocean, about the limits of our control, about the importance of humility when confronting natural systems we don't fully understand. When I started this, I said we were going to explore hydrostatic pressure, the force we cannot replicate. We've done that. We've seen why it's unique, why it's special, why it matters. The ocean's pressure is more than just a measurement. It's a fundamental characteristic of Earth's largest ecosystem. It's a barrier to human expansion. It's a driver of evolution and adaptation. It's a reminder that nature operates on scales we can barely imagine, let alone recreate. The next time you're at the beach, standing at the edge of the ocean, looking out at the water, remember what's beneath the surface. Remember that just a few miles down, there's a world of crushing pressure, a world where water itself becomes denser, where life exists in forms adapted to conditions we cannot survive, where the weight of the ocean creates forces we cannot match. That world is part of our planet, part of Earth's story, and yet it remains alien to us, foreign, inaccessible except through the most sophisticated technology we can muster. The pressure keeps it that way. The force we cannot replicate, the force that defines the deep ocean, the force that reminds us that for all our achievements, nature still has realms that exist beyond our reach. And maybe, just maybe, that's how it should be.